Hi, Mike McGrath from Semantics here. I'd like to give a quick demonstration of our SemanticFusion core, but in this case the integrated scheduling and planner capability that we already have. The system integrates a high-level sense, communicate, act capability. Sensors can generate responses, responses can do various planning activities, and then the act carries those out again with replanning capabilities as required. In this case, we thought we'd demonstrate something which is probably quite reasonable in the real world. One, a mining scenario where we have a vertical takeoff helicopter-based UAV with two carrying slots. Those two carrying slots can carry two UGVs or a UGV and a retrieval bot. This scenario is supposed to represent a mining example where we drop the UAVs out into the field. They scan an area. They then have enough power to either scan another area or need to be taken back to base to be recharged. We can also have the UGVs fail, in which case we send out a retrieval bot to collect them and bring them back. Now, you can imagine in the real world, things may become bogged or covered in debris or captured in foliage and unable to move. And we also see this as an example of something which might apply in a military perspective or a military scenario where you have downed UAVs, which have significantly expensive electro-optics, which could be salvaged, or you may put an MAV out in a sit and stare pose, and we would like that MAV to be continuing in its watching task rather than returning home. So we'll exhaust the battery in a monitoring situation rather than return the vehicle. So we then need to retrieve it in some way. So this system will replan at the base, and I'll start the system off at this point, where it will start to collect two units. It will go out to a site. It's biased in terms of its planning to attempt to put new UGVs out on site to scan. Then it will attempt to move them from site to site, and then it'll attempt to retrieve them and repair them or repower them. Now we can also demonstrate in this case a UGV failing. So in this case we have UGV1 fail. So the system will attempt to continue its previously planned task. It'll drop the UGV and then it will come back, retrieve the repair bot, go out to site, retrieve the failed UGV, then we'll bring it back to base for repair. We allocate a 30-second repair window and then the unit will be returned. Now, we are only, in this case, replanning when we come back to base, but we could replan on every sensor update or every leg of the activity. So, UGV1 is now being retrieved by the retrieval bot. System is now coordinating to return that to the base and then have it driven to the appropriate location. System will continue on. Now, we could also have the UGV2 fail later or UGV3, or we could move into a low fuel situation when the UAV has to return to base. So in this case, perhaps we'll have UGV2 fail. System will, after it's carried out its current replan activity, deliver another UGV out to site as a priority, and then come back and retrieve that particular failed UGV. Again, there's a complex coordination task that we're carrying out here, and we also have the potential for the transport to run out of fuel, and we may need to carry out certain activities based on that. So the transport refuels when it comes back to base as well. So we should now collect the retrieval bot, take it out, collect the failed UGV, and then return to base. Now, this complex replanning is a key element of real-world activities. Now, so in this system, the planning elements include moving to the appropriate location for storage, moving to location for repair, being loaded in a number of steps onto the UAV, which aren't visible in the graphic simulation here, and then actually carrying out the movement activities as required. So that's a reasonably complex set of tasks. Now, again, on landing the UGV, if it gets stuck or it runs out of power, then we send out the retrieval bot. The retrieval bot disembarks, collects the vehicle, brings the vehicle back. Embarkation is then into the UAV. The UAV returns. Then both the units are recovered and then released and put back into play. Now, so this is a significant activity. Now, we'll point out this took us 3.5 days to build from scratch. including the graphics. Again, the SemanticFusion core is ideal for integration of information, but we also have the ability to do quite complex activities. So again, we hope you enjoy the demonstration. It's a rather interesting combination of activities, we believe. Again, very realistic of what next generation autonomous system activities will need to do. And also it shows a complex coordination activity embedded within our sensor fusion system. So as I said, we have a number of elements impacting from a behavioral model and also from a planning, scheduling activity set. Now again, because of our constraint-based equivalent in terms of our semantic core, we're able to bring into play for any particular task a semantically represented set of activities and relationships. So they could be road segments for carrying out a transport planning activity. It could be determining from a limited number of sensors what the appropriate spread for a larger size area, 10 sensors in a 20 sensor area, what's the best coverage I can get. It could be working out what containers loaded onto a vehicle for transport and delivery, or potentially what's the fastest or the safest or whatever other set of attributes you want to use to determine the optimal solution. Now again, this is tied into our capability to do real-time planning. Because we're minimizing the search space by restricting the elements we're searching through, we're able to carry out activities much faster than you would anticipate. And we also integrate that with a real-time, any answer is okay, but it's not the optimal answer, but it's a viable answer model, which is a mouthful. But basically, in the real world, I expect to be able to come up with a solution within a couple of seconds to reroute my UAV and avoid it hitting a wall. I have that 30 seconds to make a decision. I need a response in that time. Well, this is the same approach here. We're looking at the best answer we can get in a limited time frame. We also, with our Sense, Communicate, Act model, the communication phase also brings in all sensors which could potentially add viable or valuable information into the decision-making process. It excludes those beyond that. So if we have 30 seconds and it's going to take us 2 minutes to get information from a third-party source, we'll ignore that as part of the what's my best guess plan and bring in only the information we need to make that critical decision at that time. I said, this is significantly different to any other planner system that we've seen operating because A, it ties our semantic models into place, and again, utilizes our agent technologies to maximum advantage in terms of running parallel planning activities if we have the resource, but also this time-constrained element, which is a key part of our solution moving forward. So again, we hope you've enjoyed looking at this solution. It's a key aspect of the capability we can deliver in short time frames to support your UAV, UGV, in general, autonomous systems mission planning and replanning capabilities, as well as integrating the sensor information in to make this more viable in the long term. And as we've indicated in our previous video demonstrations, we believe this core capability is key for the next generation of integration of smart UAV, UGV autonomous systems within the civilian population in terms of airspace or into the road system, or any other area where people and machines need to integrate. It's not sufficient to just have sensor integration moving forward. On the vehicle, we need to have external sensor information integration happening as well. So again, a key part of our SemanticFusion core is the ability to associate information being generated by a third-party sensor to me as part of my planning process, and also to be able to dynamically add that element in and generate appropriate behavioral responses. So a soldier in the field could be monitoring a sensor associated with a UAV, which they don't directly own, but they are able to, through authorization, get access to that information. Command and control may be integrating with sensors, with information on GPS tracking of troop movements, could be looking at third-party information sets related to enemy combatants and our understanding of what their behaviours translate to. And we see this again as a key differentiator in terms of our ability to integrate multiple information sources, including threat levels. Again, because we work in a concept space, a threat level in an area is a valid and viable piece of information for determining what you want to do going forward. And you can dynamically change how the system will behave. So we've now completed exploring all the areas in our simulation. As I said, it's a complex set of interactions replanned at the base in this demonstration, but that can be replanned on every sensor update and anytime there's a change in circumstance. So look, thank you very much for your time. I hope you found this interesting. Look forward to talking to you next time. Thank you.